Hello guys, this is Paul McWhorter from TopTechBoy.com, and we are here today with lesson number 8 in our new Arduino tutorials where we are exploring the development of a non-axis inertial measurement system. What I'm going to need you to do is pour yourself a nice big mug of iced coffee, and I'm going to need you to get your gear out, and we are going to jump in and take off from where we left off in lesson number 7. Just as a reminder for those of you who want to play along at home, we are using the Adafruit BNO055 non-axis inertial measurement sensor, and we have it connected to an Arduino Nano. Let's kind of remember where we left off in lesson number 7. What we had done in lesson number 7 is we had turned on the accelerometers. We had turned on the X accelerometer, the Y accelerometer, and the Z accelerometer. And based on the data that is coming from those three accelerometers, we have been able to kind of approximate the pitch, which we call this pitch, and the role of the sensor based only on the data coming off of the accelerometers. Now we're plotting that on our serial plotter, and let's see if we can turn that back on just to remember where we left off. Let's see if it comes back to life. Okay, I do believe it came back to life, and just as a reminder, we are calling this the positive X direction coming towards the right, the positive Y direction going backwards, and then Z is pointing straight up. And so that's kind of the orientation that we are using. And what we are plotting right now is we are plotting theta, or we associate that with pitch. And if you look at this, there's two ways that we're doing it. We're calculating the pitch or approximating the pitch based on the raw acceleration data coming off of the accelerometers. And then there's a second way where we filter the data to try to get a little more stability. So here I'm plotting in bright green the unfiltered data, and in dark green the filtered data. And so if you look, I'm going to introduce a pitch. When I introduce that pitch, you can see that very quickly the unfiltered data responds. So we get a very quick signal from the unfiltered data, and the filtered data is much slower. So similarly going down, the bright green unfiltered responded very quickly, and the filtered responds very slowly. Well, why do we have the filter? We have the filter in order to filter out the noise that comes from vibration. So you can see in the unfiltered data, the device is inappropriately assigning that vibration to tilt. But if you look at the dark green, the filtered value, it is not susceptible to that vibrational error. So we ended up sort of in a box that if we want it fast and snappy, it's very susceptible to vibration. But if we make it very stable, then it's kind of slow and sluggish. So do we want it noisy or do we want it sluggish? And so what your assignment was at the end of lesson number 7 was to come up with a way that we could maybe get something that's both fast and stable. Well, I'll give you a hint. Using only the accelerometers, this is about as good as we are going to be able to do using only the accelerometers. So if we're going to do any better than this, we're going to have to turn on some more features on this chip. And specifically what we're going to look at today is we are going to look at turning on the gyros. Now, just a little background about gyros. What the gyros measure is the gyros will measure the angular velocity around the x-axis, the angular velocity about the x-axis, the angular velocity about the y-axis, and the angular velocity rotating about the z-axis. So we can get these three new numbers representing rotational velocity around x, rotational velocity around y, and rotational velocity around z. And so what we want to do is we want to change those rotational velocities into angles, positional angles for pitch, and positional angles for roll. Now, what we are going to do is we're going to keep our old acceleration numbers. Okay, we're not going to throw those out. We're going to keep those. We're going to now get those same parameters using the gyros, and then we're going to figure out how to intelligently roll those two numbers together, maybe to get the best of both worlds. So what I need you to do is I need you to catch up with where we are. If you don't have the code from lesson number 7, you can go to our website, www.toptechboy.com. I need you to search on the lesson non-axis IMU, lesson 7. That was the previous lesson. If you scroll down, you can see that I have the code there. You can copy it, and then you can go over to your Arduino IDE, paste it, and then you will be starting in the same place that we left off. Okay, you will be starting in the same place that we left off. And so everything here in this existing code is basically turning the sensor on, getting the acceleration data, and then creating those filtered and unfiltered approximations for pitch and roll. What we're going to do now is we're going to go in and we're going to see if we can get similar type numbers from the gyros. So first of all, let's do a little bit of work, a little bit of paperwork, a little bit of math to figure out how we would go from having these angular velocities to having a position. Okay, well, what is it that we want? Just like before, what we want is pitch, and we call pitch theta. Well, now, since it's a new way of calculating pitch, I think I'm going to call it theta sub g for the pitch that we're going to get from the gyro. Remember, we already got a pitch from the accelerometer, but this is going to be a different one, the pitch from the gyro. Well, what would the pitch from the gyro be if we have angular velocity? Well, it would be wherever we were before, okay? So the new pitch is equal to the old pitch plus how fast we're spinning times the change in time. Now, you can kind of think of this as sort of like distance is equal to rate times time, like how far did I go? Well, if I'm going 60 miles an hour, and since my last measurement, if I've gone an hour, then 60 miles an hour times an hour, I've gone 60 miles. So it's the same thing, only instead of linear distance, this is rotational velocity, and then you end up with an angle. So we're going to say that the pitch, or theta, coming from the gyro is equal to whatever our old value was plus, in the last increment of time, how fast we were spinning times the change in time. Well, where do we get this from? Well, we get this from the gyro because it measures angular velocity. And specifically, if we want pitch, that is rotation about the y-axis. So we need to look at the rotational velocity coming from the y gyro. I hope that makes sense. What else do we want? We want the phi, and the phi is the roll. Well, what would the phi from the gyro be? Remember, we already calculated phi from the accelerometer, but this is a new way to do it. Phi from the gyro is equal to whatever we were at before from the gyro plus omega. And again, if we're looking at roll is rotating around what axis? Around the x-axis, so it would be omega x times the change in time. Okay, so these are the new calculations that we're going to do. But in order to do this, I need to turn the gyros on so that I can get the omega about the y-axis and the omega, the rotational velocity, about the x-axis. So let's go in and let's go back to our code view and let's see if we can start getting this to work, okay? And we'll sit here and we will look at these equations because they will be quite helpful as we are trying to develop this. Let me see if I can get it to focus a little better for you, and that's pretty good. Okay, so we're here in our code view, and all of this code earlier that we developed, what it's doing is it's creating those approximations for pitch and roll from the accelerometer, and then it's creating a filtered pitch and roll from the accelerometer. So now we're going to add some more stuff to it. And so let me get my windows called up here and get kind of oriented to what I'm going to do. The first thing I want to do is I just want to turn that those gyros on so that we're getting a gyro measurement. And the best place to do that is we can come down here in the void loop, and you remember this command where we said IMU : go get a vector, and you want to call that vector your acceleration vector, and then you want to get the accelerometer vector. Well, we want to do the same thing. We want to keep doing this, but now we also want to get the gyroscope vector. And so we're going to take this line of code and we're going to copy it, and then we're going to come here and we're going to make a second pull of data from that, but this time instead of getting vector accelerometer, we are going to get vector gyroscope. Okay, gyroscope. I hope I spelled that right. And now, what word do we want to put that data in? We don't want to call it ACC because that's where we're putting the accelerometer data. We'll call this GYR. So with this, I should get the 3-axis of acceleration, which I already was, and now I should be getting the 3-axis of gyro, okay? And so I think the first thing I want to do is just come down and print it and see if I'm actually able to bring this thing to life and get data off of it. So remember all the things we were printing earlier, now we are going to print some new stuff, and since we're adding stuff, remember only the last of our prints do we want the LN on. So I'll put a blank line just to remember what we're adding. Serial.print. And what do I want to print? I got to print my delimiter, a comma. And now I'm going to do a serial.print, and I'm going to print, let's print the acceleration, or no, the gyro data that we just took. And let's see, for pitch, that would be acceleration about y. Angular velocity about y. And so we'll do y first. And then I need another delimiter, another comma. Okay. And now serial.print. This will be the last one, ln. And I want to print the gyro about x this time, because about x will give us something that would be related to roll. And I'll close that up, close it. Let's try to download. Please hold your breath as we try to download this up. I got to make sure also that I have my serial plotter turned off, because remember, you can only have one thing touching that serial port at a time. All right, let's see if we can download. It's going to work. It's going to work. I know it's going to work. It's going to work. Okay, so that looks good. So let's go back to our serial plotter, which I believe this is a good view of it here. And now let's remember that we just added two more data channels. And so over here, I need to go to data format down here. And instead of 11 channels, now I have 13 channels. Okay, now we need to come over to plot, and then we need to label those new channels. This was what was it? This was y velocity, the y angular velocity, and then it was the x angular velocity. So we'll just add those two. And then the only thing I'm going to plot are those gyro values that we just pulled. So if I'm not mistaken, when I turn this thing on, I should be looking at rotational velocity. And so let me get this back in your view here. And this should be y velocity because that's rotating about the y-axis, and this should be x velocity because that is rotating about the x-axis. So let's see if we can turn this thing back on. And I do believe it has come to life. And so I would expect the red to be the pitch. And so let me kind of pitch this thing and look at that. Boom! I am measuring rotational velocity, but I want you to notice something. I'm going to tilt it and I'm going to stop. Okay, I'm going to tilt it and I'm going to stop. Do you see now there is no velocity, so it doesn't show any velocity. This is not measuring angle. It is measuring angular velocity. Similarly, let's look at the light blue as I'm going to rotate like a roll, a rotation about the x-axis. Okay, look at that. Very nice signal, but it's measuring velocity. So when I take it away, it comes back to 0 because there's no velocity. I need to change that rotational velocity. I need to change the rotational velocity into a rotational angle. So how would we do that? Well, I'm going to first turn this off. So I go up to open and I click on it. So I'm releasing my serial port, and let's go back to a code view. All right. So first of all, I think we are going to need some new variables. And so let's come up here to the code and let's see if we can introduce some new variables. The good news is we're getting the data off of the gyro. We're talking to the gyros, we've activated, and we're getting data off of them. But what we need to do now is we need to start doing something with those, and so we're going to have to put in some new variables. And so let's see here. We have, this is where we left off before, the phi filtered. That was the phi from the accelerometer. And so what we're going to need is we are going to need a theta. That is the parameter that we associate with pitch, the theta. But this time we're going to get it from the gyro, so we're going to call it theta g, and we'll give it a value to start with. You just got to start it somewhere. We'll say 0. And then float, just like we have a theta associated with pitch, we're going to have a phi associated with roll, and so we'll call it phi. And then where are we getting this one from? This one's coming from the gyro, and we're going to say 0. Okay. Now we're also going to need to think about time. Okay. So we got to kind of think about this concept of dt, and so we have this theta g. Let me get it where you can see it. We've got this theta g, we've defined that variable, and it's equal to the theta g, wherever you were before, times the angular velocity. Where did we get that? Well, that's that gyro y value, right? That gyr dot y. Okay, so we have this from the gyro, and now we need a dt, a change in time. Okay, we need a change in time. So we're going to come here and we are going to define a variable which we are going to call a float, and it's going to be dt. That is the change in time, this dt, this change in time from our last measurement. Okay, and then also we are going to need something where, right, with millis, if we use the millis command, that'll show us where the system clock is, but we need to have a marker of where the clock was last time around. And so we need to make that in the same type of variable that the millis is. The millis system command, strangely, is in a unsigned long. And so to make this thing work right, we need to dimension this variable as an unsigned long, and this is my millis old. And this is just a place marker where we can hold that timer so we can use it the next time around. All right. And so what is dt going to be? dt is going to be the present milliseconds minus the milliseconds old where I was before. All right, so every time through the loop it'll calculate a new dt. I hope that makes sense. Okay, I hope that makes sense. Now, one of the things that we need to do is in our void setup, we've got to start this millis old somewhere so we'll not get a crazy number the first time through. And so we will actually do that at the end of our void setup. We'll just populate that millis old and just make it millis. All right. Now, why do we do that? So that the first time we use this variable, we have something in it, and the first time it's in the loop minus this value. Okay, hopefully this will make a little bit more sense in a second, but what am I trying to get? I'm trying to get dt, the elapsed time between subsequent measurements. So I think this will make a little bit more sense when we get down here. Okay, so first thing we want to do is we want to make the measurement. The measurement has been made. Then we do all of this nonsense associated with the accelerometer, getting the filtered tilt and the unfiltered tilt, or the filtered pitch, the unfiltered pitch, the filtered roll, the unfiltered roll. All of that was in lesson number 7. But now we need to do a calculation based on the gyro. Well, what do we want? We want these equations here. So we are going to say theta. I guess the first thing we should do is calculate dt. And so dt is going to be equal to millis, that's where the present clock is, minus what? Minus the old value, millis old. So if I take the present minus the old one, that will be the change. What we have to remember is this crazy millis measures milliseconds, so we need to change that to seconds. How would you change milliseconds to seconds? You would divide by 1,000. And to make sure I keep it afloat, I'm going to put the point there. If you don't put the point there, you might get some crazy integer math going on, so I always use the decimal in a case like that. Okay, so now we have a dt. Okay, before we go on, we've got the dt that we need, but before we go on, we got to remember where millis was. And so millis old now is going to be millis. So we're grabbing the existing millis as millis old so we can use it the next time around. Okay, think about this. What we're trying to do is measure the increment of time dt between one measurement and the next. And so I've got to grab where my system clock is now so I can subtract it the next time around. Okay, so we will put our semicolon there. We now have a good dt. We have a good dt, and we are queued up, ready to calculate the dt the next time around because we grabbed the millis old. Now we are ready to do a calculation. And what we want is we want that theta g. And what is theta g? This theta g is equal to what? The old theta g. The old theta g plus what? Plus the value coming off of the gyro. So what was that? GYR. And if I'm going to do pitch first, which we call theta, nose up we call pitch. If I'm going to do that, that is rotation around the y-axis. So this is going to be that y value that we're going to use here. Y, open, close. And then times what? Times dt. Now, similarly, we're going to need a phi g, and that phi g is equal to phi g, our old phi g, plus, okay, now a roll is rotation around the x-axis. So we're going to want gyro dot x this time, and again times dt. All right, I do believe that I have theta g, and I do believe that I have phi g, so I have got a new way of approximating pitch, and I have a new way of approximating roll. And so let's go in and let's look at those, or let's see if we can download this. But I do need to print these so that it will plot them. So I need to print these two things. So if I come down here, I don't need this gyro y value anymore because I know my gyro is working. So I'm going to make this theta g. And then this will be phi, if I can, phi PHI-G. And I hope I did that right up here. Yeah, PHI, phi G. Okay, so that should give me, now instead of getting a rotational velocity, this should give me a rotational angle. It should actually give me the angle. And so let's see if we can download this. Yes, yes, yes. Download, yes. Okay, yes. All right, so it downloaded. We don't know if it's right or not, but at least it downloaded. So let's come back over here and remember now that this channel 12 is no longer y velocity, but it would be theta from the gyro, and then this channel 13, the last one, is not x velocity anymore, it's phi from the gyro. Okay, so let's see if we can turn this thing on now. I'm sorry, you guys didn't see that. Let me move over and I'll redo that real quick. Remember now these last two channels, this is no longer x velocity and y velocity. It was theta from the gyro. Remember, theta is pitch, or related to pitch, and phi is related to roll. And I hate it when I lose this focus. Okay, that looks pretty good. So now, when I turn these on, I should be looking at not velocity, but I should be looking at angle. And so I'm going to clear this, and I'm going to turn this on. And let's see if this thing gives us anything reasonable at all. So I'm going to say open and hope this comes to life and hope I see something reasonable. And I am not sure I'm seeing any. Okay, yeah. All right, so now remember the first one, theta in red, should be pitch. And so I'm going to pitch my nose up and look at that. That comes right up, down, and down. Now let's try nose down, negative pitch, nose up, positive pitch. Now let's try a roll. Look at that. Okay, and let's try a roll. The one thing I don't like is that we'd sort of define that the left, this edge up, is positive in our orientation system, and you can see that we're kind of oriented backwards. The pitch is right, the nose up is positive and the nose down is negative, but our axes are sort of reversed, and so we need to go in and adjust that code just to make sure that we're keeping the same direction and the same up being up. Focus, you aggravating thing. Why does this thing get so confused sometimes? Well, it really doesn't want to focus, does it? Let me get that focus before we go on, because you guys really need to see this as we move on. Okay, there we go. That looks good. Okay, so let's go back to our code view and let's take care of that problem that we kind of got the opposite sign of what the system is using. And so we need to make that adjustment. And I think the easiest place to make the adjustment would be to just say that it was in the roll, which was the phi, is phi, and just put the minus sign here. And I think that that will fix it if I'm not mistaken. I got to make sure that the serial plotter is off, and then I got to come back to my code view. Let's see if this will download. I think it's going to download. I will move my keyboard out of the way, and we are going to come back to the serial plotter, and I'm just going to reset this thing, and I'm going to clear this thing, and now let's see if we can turn this back on. I'm sorry, you guys aren't seeing this, but that's okay. I wasn't really doing anything. I just hit clear up here to get the old data off, and now I'm going to click open to see if I can bring this thing back to life. Okay, it has come to life. So I'm going to introduce about a 45-degree pitch. Okay, and look at that. That looks pretty good. I let it go back down. It goes down. Now I'm going to introduce a roll. Look at that. Back down, a roll, back down. Now I'm getting pitch, and roll from the gyro alone. Boom! Okay, now let's see if this is susceptible to vibration. Look at that, not susceptible to vibration. Okay, so what do I love about the gyro? I love that it gives me an orientation for pitch and for roll that does not depend on the accelerometer and is not susceptible to noise. Okay, but somebody tell me what is wrong. Okay, didn't have any noise, but what do I see happening up here? What do I see happening? It is not moving and I have a drift error. Do you see on this roll component, it is saying that it is at like minus 15 degrees, and it is in fact saying the pitch is like at minus 5 degrees. So what is the problem with the gyro? Like, why would we not just go throw the accelerometer away? We would not throw the accelerometer away because the accelerometer has no drift. The accelerometer has noise. What do we see about the gyro? The gyro has no noise, but it has drift. Okay, do you see as it sits here, you start getting errors in the signal? So what we've got is, we've got an interesting situation. The accelerometer by itself, like let's go in and let's look at those. Okay, I'm going to turn on the accelerometer again, and I'm going to do the unfiltered values. So that would be theta and phi as we labeled them before. So now when I do pitch, do you see I'm getting a pitch from the accelerometer and I'm getting a pitch from the gyro. I'm going to do roll. I'm getting a roll from the accelerometer and a roll from the gyro. But now let's look at what happens. The accelerometer is susceptible to vibration, okay? But when I bring the accelerometer up, okay, that is that green, that bright green, there is no drift in that while there is drift in the gyro. So do you see, I've got pitch from the accelerometer, pitch from the gyro. I've got roll from the accelerometer, I've got roll from the gyro. Each one has its pros and cons, okay? So what's your assignment for lesson number 9 is, how do you take advantage, like how do you take the best of both worlds, and how do you fuse these two signals together where I have the low drift that I like associated with the accelerometer, but I have the low noise that I like associated with the gyro. I want to fuse these two data streams together to get something that is both quick and snappy. Okay, I want it to be quick and snappy, and at the same time, I want it to not be susceptible to vibration. Does this make sense? Okay, I think this is a pretty cool lesson. And man, lesson number 9 is going to be sensor fusion. And you guys really need to think about this before you do it. See if you can do the homework on your own. See if you can fuse accelerometer and gyro data together to get something that really works well. All right, guys, this is Paul McWhorter from TopTechBoy.com. If you like these lessons, think about giving us a thumbs up. Think about subscribing to the channel. Share this with other people. I will talk to you guys later.